Hello everyone again, and welcome to this particular video where we're going to be looking at a specific device which is quite remarkable, I would say, in the world of applied physics, called a cyclotron. And a cyclotron in here, looking at what we're going to dive into in this particular video, is that we are going to explore how cyclotron works, and our goal in this video is that we will be able to identify any functioning cyclotron, and this actually leads into deriving period and maximum kinetic energy of a particular cyclotron, and finally lead to a conclusion on how this is applicable in the world of applied physics. So now let's look at what a cyclotron is. Cyclotron is a machine that can accelerate charged particles outwards from the center along a spiral path to a very high velocity, and this was actually developed, I would say, by two set of guys. One is Ernest or Lawrence, and the other is M. Sterling Livingston, and these two guys paved the role for this particular machine that you see beside them. The guy with the gray suit in here, looking at it in this photo here, is actually Ernest O. Lawrence, and he actually won the Nobel Prize in Physics in 1939 for his contribution to the creation of a cyclotron and how this led into radioactive activity in there. So looking at how this structure is actually set up here, we have this particular curved metal part which contains a magnetic core, and these two cylindrical metals are actually regions where we actually have a large box containing a coil of wires that create the magnetic field, and this magnetic field is important alongside the vacuum which is noticed between these two cylindrical container or boxes. And this vacuum here contains the D's, where we have the oscillator influencing the creation of the electric field that influences the charged particle in that spiral motion. So looking at the structural functionality, we have sets of two magnetic cylindrical containers that creates the magnetic field. We have this actually being the combination of the north and south, and this next compartment deals with the 2Ds which are found inside the vacuum, and this is one D that we see on the left and the other D is actually seen on the right. And these 2Ds, D1 and D2, when connected to an oscillator which actually provides alternative voltage, and this actually leads to the increase in high speed, which is resulting in that particle moving in a specific direction. Now in this case here, we're going to have particle that is injected into the combination of those two fields, and this particle could either be a proton or electron. In this case, if it is an electron, an electron will actually move in a specific direction. If it's the proton, it will move in the opposite direction, but it will be in a spiral motion. So the green actually shows or tells us that, hey, we need to measure that kinetic energy of that particular particle at that particular instant. So this is actually a nice way to measure both the velocity and the kinetic energy, and this little barrier is known to be the vacuum, where the particle and the D's are actually located in. So looking at this structural functionality, looking closely, we see that these 2Ds actually, with the combination of the oscillator, actually leads alongside the electromagnetic poles to the particles, and this influencing the particle motion that we are going to focus on arrives at a specific conclusion that there will be a high speed generated by the particle when the particle is in the combination of both the electromagnetic poles and the 2Ds. And this high speed is actually going to be detected by a detector. So this actually generates or measures both the velocity of that particular particle and finally the kinetic energy, which is represented as K max. So looking at these in here, we're going to determine the kinetic energy or maximum kinetic energy. And to determine the maximum kinetic energy of a particular particle, specifically a charged particle, we need a 2Ds, D1, D2, and the oscillator that provides the alternative voltage V, and we need the electromagnetic poles which provides the magnetic field. And the combination of the 2Ds when an oscillator is introduced is actually noticed to be in the semicircular container. So these 2Ds are pretty much semicircular containers where D1 is one half and the other one, which is D2, is the other half. And these semicircular containers generate what we know to be a high frequency, where this high frequency leads to the voltage that is applied when the oscillator is injected or influencing that generation of the high frequency. And the combination of the 2Ds that generates the high frequency and the electromagnetic poles which provides the magnetic field creates a setup that shows a perpendicular arrangement between both the magnetic field and the Ds. So this leads to a high increase in the force that is applied, because due to the right hand rule, we know that the magnetic field or the velocity of a particle perpendicular to the magnetic field actually leads to a cross product where sine 90 is actually resulting in the maximum speed or maximum force applied. So this particle here, which is either a proton or an electron that comes out of ionic source, in this case we'll look at a proton, and by calculations we will generate a specific conversion for the motion of that particular spiral path with respect to the specific charge of that particle. So in this case here, if we decide to pick a clockwise direction for a positive particle, then it means that it will move in the spiral path that is clockwise and then finally hits the target as time goes on. So that motion, which is a spiral motion, we need to determine the period and finally determine the radius of the circular path. And this actually to determine the period of one revolution of that particular particle path, all we need to recognize is that this actually revolution tells us that half of that particular period actually gives us a polarity of the voltage to be reverse. So as we go half a period, the polarity of the voltage is reverse, which means that we're going to go from D2 to D1. It means that you need half a period to go from D2 to D1. Therefore, there is a gain in energy going from D2 to D1 for every half a period. That is one thing you should remember. Now, how about the period? What is actually T? And to determine what T is, all we need to do is to recognize that the T has to be the charged particle, in this case the proton, in an active cyclotron. And an active cyclotron means that you are not only combining the electromagnetic field, which is represented as B, which is the magnetic field, but also the electrical or the D's field that is generated. So once you have those combined in here, let's start looking at for conversion, we have a specific proton, and that proton is already provided, or there's also a force that is provided already, and this force provided is a combination of the magnetic field and the electrical field. So in here we see that the particle, which is a proton, moves in a counterclockwise direction. That is a conversion that we are going to set in here. And so if it moves in a counterclockwise direction, it means that the velocity is pointing in that direction, and this velocity of that particle is actually perpendicular to the magnetic field, which is pointing towards us. So in this case, we actually determine our angle between the velocity and the magnetic field to be equal to 90 degrees. And if you apply that to the cross product, which gives us the force, this actually gives us exactly a magnitude or constant that is a product of the charge, quantity of charge, multiplied by the velocity and the magnetic field. So this actually constant is actually perpendicular in this case to the velocity of that particular particle, which means here that for conversion, if Q is greater than 0, it means that it's moving in a counterclockwise direction, which in this case is a proton, while if the quantity of charge is a negative value, which means that it is less than 0, it means that the direction of the spiral path is actually in the clockwise direction, which in this case, or that case, will be an electron. So looking at this, we need to introduce the centripetal force, and the centripetal force has to be equal to that of the magnetic field force. And in this case, using the Newton's second law of motion to determine the centripetal force, it means that since ma is equal to a, which is noticed to be the square of the velocity divided by the radius of the circular path, this actually multiplied by the mass gives us the centripetal force. So since the centripetal force equals to the magnetic force, this actually, or electromagnetic force, this is actually equal to the mass multiplied by the velocity square over r, which signifies the centripetal force, and this is equal to the constant, which is the quantity of charge, which is in this case a proton, multiplied by the velocity times the magnetic field. So in this case, solving for r, we actually determine r to be the radius of the circular path, which is equal to the mass times the velocity divided by the product of the quantity of charge and the magnetic field. So once we've determined the radius of the circular path, in this case the next path is to determine what the period based on the angular velocity, and the angular velocity we notice is equal to the velocity of that particle divided by the radius of the path. And since we put this in equation 1, which is the radius of the path, we can actually express this equation, which is equation 1, in terms of the angular velocity. So in this case, solving this particular expression, it means that the denominator has fraction. That means that you have to flip the numerator and denominators, and we're going to get our angular velocity in terms of not only the quantity of charge but the magnetic field and the mass. Therefore, the angular velocity is not dependent on the radius and the velocity of that particular particle in that particular d's. So in this case, since we have our conclusion for the angular velocity, which is pretty much the cyclotron angular velocity, in this case we can actually determine the period. And to determine the period of motion, which is represented as t, it means that t in this case is equal to the circumference divided by the velocity, where we know that the r divided by v is equal to the reciprocal of the angular velocity. So therefore, since our period is in terms of the angular velocity, we put that equation into the period equation, and we actually get our period expression, which is in terms of the mass, the quantity of charge, and the magnetic field. Therefore, the period of the particle of a cyclotron is actually independent of that particular velocity and the radius of the path. So since we notice that if there's any other questions that might be introduced, something like the cyclotron frequency, how can you determine that? We know that the frequency is a reciprocal of the period. So if you just put in the period expression into the frequency, we can actually determine the expression for the cyclotron frequency, which is a reciprocal of the period cyclotron period. So now, using the period, how can you determine the kinetic energy? Since we know that the period doesn't depend on the velocity and the radius, it means that in this case, if we have our 2Ds, and these 2Ds are positioned right here, and we introduce our oscillator, which generates the alternative voltage, or in this case, once that is applied, we have those field introduced, where we have that gold representing the magnetic field, and we have all those lines which are blue between the two D's representing the electrical field. This actually is perpendicular to each other, and once you introduce an ion source that will release a proton, and we plot our graph with the 2Ds with respect to the time or period, what we see is that for a particular circular path going from that original source to the first D2 going to D1, we have that particular graph being plotted that goes all the way to the crest, and then from the crest we actually have an increase in kinetic energy that lets that particle to move faster and makes another spiral path, which is equal to a period in this case. Well, it's half a period in this case right there, and then there's another gaining energy that actually makes that particle to move again to another half a period, and this goes on. And so if you have a full period in here, half a period is actually needed for you to gain energy, which is noticed from D2 all the way to D1. So in here, the voltage reverses, which actually tells us that there is an increase in the kinetic energy, and therefore what is the maximal kinetic energy? Since we know that the radius of the D's is represented as the capital D, in here we can actually state our forces to be equal to each other, which is the centripetal force and the electromagnetic force. Therefore, in here we have our expression, which is the mass multiplied by the velocity squared over the radius of the D's, which is equal to the quantity of charge multiplied by the velocity of the particle times the magnetic field. Therefore, solving for the velocity, we can actually get our velocity to be equal to the quantity of charge times the magnetic field times the radius of the D's divided by the mass of that charged particle, which in this case is a proton. Now, since we know that classically the kinetic energy maximum is equal to half mv squared, since we know our v to be equal to the quantity of charge times b times r divided by m, we can put that into this equation, and we'll be able to arrive at the kinetic energy maximum, which in this case is expressed as q squared b squared r squared over 2m. where m is the mass of the particle and the quantity of charge represented as q, and b represents the magnetic field, and r is the radius of the Ds. So this is actually needed in order for we to determine the kinetic energy of that particular particle. So therefore, in conclusion, the kinetic energy in here, which is represented as that expression, is actually working, or it works when the kinetic energy maximum is less than 20 mega electron volts, which in this case actually the relativistic effect is actually negligible enough for this particular expression to not be dependent on the velocity and the radius of the circular path. However, if your kinetic energy is greater than or equal to 20 mega electron volts, this actually tells us in this case that our relativistic effect is actually non-negligible. Therefore, the mass is actually going to be equal to the mass and the velocity, which is pretty much the momentum. So this is something to take note of, where we know that the work when kinetic energy is less than 20 mega electron volts actually tells us that the frequency remains constant, but the acceleration increases as the distance covered actually increases. So looking at examples of this particular machine, we have the Fermi National Accelerator Laboratory, which is the Fermilab. This is actually located in Batavia, Illinois, in the United States. And if you look closely at the GPS map, we see two circles, where one circle here we notice to be called the main injector ring, and the other big circle here is actually called the Cyclotron, and this actually is currently inactive since 2011. And this actually combination here actually accelerates an antiprotons that actually is energized to roughly 400 to maximum 500 giga electron volts, which is really massive. It's like having 11 zeros after 4, which is massive right there. And this actually produces a proton-proton collisions with energies of around 1.6 tera electron volts, which is really a big amount of energy released in this case. And the first accelerator to reach this is actually the first accelerator to reach a tera electron volt, which is way bigger than that of giga electron volts. So the radius, looking at this, is determined based on the circumference, and the circumference of this particular, I would say, accelerator is around 3.9 miles, or approximately 6.3 kilometers, which is pretty much the fourth largest particle accelerator in circumference in the world. So the other one, which is the first and the largest in the world, is called the Large Hadron Collider. And this is actually located in Switzerland, between the borders of Switzerland and France, near Geneva. And this here has a circumference of around 27 kilometers, and the tunnel depth is around 175 meters, which is around 574 feet. And this shows two circles as well, where one circle, which is a large one, is actually where the colliding protons or heavy ions takes place, while the small circle, which is inside the big circle, is actually known to be called the superproton cyclotron. And this actually has so much high energy, where relativistic effects actually plays a role in the kinetic energy maximum, and this actually accelerates protons or ions. So in here, the collaborators in creating this largest machine was actually done by the European Organization of Nuclear Research, and this was done between the year 1998 to 2008, with over 1 or 10,000 scientists plus 100 of laboratories and universities plus greater than 100 countries coming together to create this massive machine, which is really magnificent. And the biggest achievement here was that the first collision was achieved in 2010, and that was pretty much 2 years after, and this energy released was around 3.5 tera electron volts per beam, and this is actually this is pretty much 4 times larger than the previous world record, and this is around after an upgrade that it reached 6.5 tera electron volts per beam. So it's really massive to see this play out, not only for this construction of collider, but how this is a great upgrade from the previous machine that we talked about. And finally here is that this actually at the end of 2018 is entering a 2-year shutdown period for further upgrades. So for future upgrades, this will lead into more research into reactors and also how different new particles might be generated due to different types of collision, where we can actually subject various subatomic particles to higher collision and see whether there are other subatomic or nuclear particles that may be, discovered, not now but in the future. So that's about it for this particular video. Hope you're able to understand how a cyclotron works and how to determine or use the period and the maximum kinetic energy to determine how various particles are actually influenced in various chemical or nuclear reactions. And hope to see you on the next video. All the same, stay smart and believe in yourselves.